diffraction. Okay? Okay, diffraction was when you put a wave through slits. The waves interfere with each other, and they make that interference pattern. Okay? So the fact that you see a rainbow is just an interference pattern. The rainbow is an interference pattern. Okay? The rainbow is an interference pattern. So, and I found a second animation that does a little bit better job of showing it. And so, all right, so here they got light waves. They go through a slit. Those waves interfere with each other, and they add up in different places. Okay, right here they're going to add up, and right in between there's a place where they always cancel each other out. There's going to be an angle where the top of one and the bottom of the other always add up, because it's a curve, right? So there'll be an angle, and you'll get this pattern, a pattern of dark, light, light in the middle, dark on both sides, then another band of light, then dark, alternating light and dark. Okay. So notice I picked green light, and notice what happens when I change the wavelength of the light. That when I go to the red, the spaces move further out. Okay? And when I go towards the blue and the violet, they get closer together. So that's why when you look at the diffraction grating, you're going to see all the colors are going to add up down the middle, so you're still going to see the thing that you're looking at. You can still see the light. It didn't take all the light, it just took some of it. So it was a little bit dimmer when you put the diffraction grating in front of it. Right? You still see the basic thing. But the first one you were going to run into outside of the middle is where purple adds up. Right? And then a little bit further out, blue will add up. And then green, and then yellow, and then orange, and then red. And this red right here, well, this area is all black, so the second violet is ready to be there. So you get the second rainbow. So when I projected it, we could see the two different rainbows off the side. When you look at this diffraction grating, you could see that second set of lines off to the side. That's because it always adds up here, everything, and then the violet adds up, then the blue, red, orange, green, yellow, and then right about here, once you hit red, the next violet adds up. Does that make sense? Okay, so that can only happen if you start with a wave. Okay? Because only a wave can go through both holes at the same time. Okay? Light is a wave. Well, very quickly earlier this week, we mentioned de Broglie and said he came up with the equation for a wave for stuff. De Broglie. He said he put together some equations, got the equation for the wavelength of a particle. Okay? So, we're never going to have to solve it. You don't know calculus, you can't solve it. Okay, but, what will an electron do? Okay? Okay? Because if I shoot at two slits, different things happen with particles and waves. Because if an electron is a particle, it can go through the slit on the right or the slit on the left. And you're only going to get two spots where it hits. And it'll be dark in the middle. Does that make sense? If it goes through both, like a wave, it'll make an interference pattern. So while it sounds bizarre, we've looked at the two tests that show that light is a wave and light is a particle. The photoelectric effect is only explained because light is a particle. that you have to have a big enough particle of energy to knock the electron off. The more of those you put in, the brighter it's going to be. If you don't have any, if none of them are big enough, you can't add them up to get big enough. None of the electrons get knocked off. 3-year-olds are never going to make a basket, right? That's proof that light is a particle. The rainbow is light. That light is a wave. Which one is it? The answer is yes. It has both wave and particle natures. It's not a wave of particles. The particle itself is a wave. Okay. So here's the idea of the two different results. It's got an electron gun, and if it's a particle, it'll go through one hole or the other. And if they're shooting guns, you want to stand right here. Does that make sense? Okay. You want to stand right there. Okay. Now, if the gun is a wave, if the electron is a wave, it's going to go through both holes at the same time. Okay. And over time, you'll gradually build up an interference pattern. Okay. So if it's a wave, we get bunches of spots, including hitting right behind it. Notice how the light does hit the middle. Right? So they got an experiment. All they have to do is find slits that are small enough to try to fit a light wave through. Yeah.
Can you explain why it isn't like completely white?
Because it's a wave.
Oh yeah.
Okay, so it's doing the diffraction. If it's a wave, it's going to do that. If it's a particle, it's going to make two spots. Okay. So what did it do? Well, they had to find some place where they could get little narrow scratches, narrower than I can make in that plastic. And what they found was the gap between atoms in aluminum was the right size. Okay? It's a tiny little gap. Okay? And these two pictures changed physics. Okay, so they put aluminum at the center and they shot X-rays at it. And they got this pattern. That as the X-rays went through that aluminum, they interfered with each other and see the alternating bright and dark. Okay? So the X-rays are light. They make an interference pattern. Does that make sense? This is just like those bars on the other one, except it's circular, because you can't aim flat. Okay? You can't do it in 2 dimensions, got to do it in 3. Right? This is what happened when they shot electrons. See the interference pattern? See how that picture is like that picture? That means the thing that made this is the same kind of stuff that made this. The electron, it made an interference pattern. It made an interference pattern. The electron is a wave. The electron's a wave. The electron is both a particle and a wave. Okay, if your mind's not twisted now, it should be. You've been okay, so what do they mean it's a wave? Well, it's a special kind of wave called a standing wave. Okay? A standing wave is one that doesn't move because it's got the right frequency and pitch. Okay? So, give you an idea what a standing wave was. And it's actually going to solve one of Bohr's problems. Okay, so when Bohr, with his atom, if you asked him where are the electrons allowed to be, they said they're allowed to be in certain energy levels. Right? They're allowed to be in certain energy levels. It says, why are they allowed to be only allowed to be in certain energy levels? And his response was, because that's only allowed. That's all that's allowed. Why is that? Because that's all that can ever happen. It was like a law. He knew from the pictures, from the spectrum, that it was true. He didn't know why. He couldn't explain why there were energy levels. Okay? Couldn't explain why the planet Earth is gradually spiraling into the sun. Why isn't the electron gradually spiraling into the nucleus? Okay? Well, because it can't change that energy level. But if you treat the electron as a standing wave, it's very quick to see why you have to have whole numbers of energy levels, that you can't have half an energy level. So let me build a standing wave for you if I can. So I'm not going to hit you, Katie. Okay, so I got a wave here, right? But if I change the frequency, I can make it 2 waves or 3. That was 3. There's 2. Can I do 1.5? Is 1.5 going to work? It's got to be a whole number. That is why there's energy levels. The first energy level is 1 whole wave. The second energy level is 2 whole waves. The third energy level is 3 whole waves. The fourth energy level is 4 whole waves. So if you treat them as waves, you got an explanation for why there's energy levels. So that picture changed our view of the universe, because it said the electron's a wave. Okay? And not just the electron's a wave. They've tried it with bigger stuff. They tried it with protons. The proton's a wave. They tried it with whole atoms. The hydrogen atom's a wave. That's where we're going to. What does the model look like? All matter is waves. Both particle. You are a wave. You just have a very, very short wavelength. Okay? Okay, so not only is energy both a particle and a wave, matter is both a particle and a wave. Hey, it's freaky. And nobody wants to believe. You know who fought this idea? Einstein. Einstein fought against this until he died. Because it worked, but he didn't like it. Because it wasn't, okay, because what you lose is causality. If this, then that. Because when you get to what the electron's really like, all you're going to be able to say is, if then you got a good chance of that. And we start talking about probabilities. Okay. Okay. So this led to Schrodinger's equation. Schrodinger. Sometimes they put an E after that, depends on how they translate the German. But I did get to type the umlaut, so I'm always happy when I get to type an umlaut. Everybody knows the umlaut is the 2 dots on top, right? And it's a cool word to say. Okay, now Schrodinger, what he did, he wrote the equation for the electron as a wave. Oh, yeah, that's right. Okay. Okay. Oh, no, Schrodinger's cat is based on that probability idea. We'll talk about Schrodinger's cat later. Or will we? Okay. Now, the quantum mechanical model is the application of Schrodinger's equations. Okay. Good news for you. You will not have to solve Schrodinger's equation. Okay, and here's why. Okay, the first time I saw Schrodinger's equation was when I was in my 4th semester of calculus. And the first thing we did with that equation was prove you can't solve it. Unless you're familiar with some radial, it's not in X, Y, and Z, it's in R, theta, and phi, 3-dimensional polar coordinates. You guys want to talk about 3-dimensional polar coordinates? We'll probably not do that. We probably wasted time right now, okay? Okay, but we've proved that you couldn't solve it, okay? But just because you can't solve an equation doesn't mean you can't get information out of it.
How does he make it? Yeah.
No, you can write lots of equations that can't be solved. No. Where the two sides are equal, but you can't find the unknown. Okay. But what you can do with an equation like that is, if you compare its squares in a specific way, what you can find out is the probability that your answer is there between these numbers. Oh, no. Because I can calculate the probability of where the electron's going to be. That's what I want to do. I want to know where the electron is. Okay. So it's called the quantum mechanical model because it still has that idea of quanta from Bohr. Little pieces of light that make it jump from energy level to energy level. But now our energy levels are not what we thought they were before. Quantum is a specific chunk. Quantum means chunk. A photon is a light quanta. Yeah, Latin root. No, it's not a problem. It's, you don't know enough. You don't know enough to read the format of it. Okay. So he derived an equation that described the energy and position of the electrons. Okay. And it was calculated in a way of it would be this distance at this angle and at this angle, r, theta, and phi, instead of x, y, and z. Different way of mapping three dimensions. Graphing. You're used to doing graphing by x and y. You can also do it by how far away from the center it is, what angle it is. That's the other way of doing polar coordinates. If you haven't done them yet, they're really cool.
Isn't that other dimension like the diagonal?
So and the diagonal and the other ones, and you do the second one by saying what angle it is on the other plane. Yeah. And treat electrons as waves. Okay. Couldn't solve it, but he could get probabilities out of it. Okay. So electrons are waves. And here I've got some bad news for you. It's just a mathematical solution. It's not like anything you have seen before. And it's not like anything that you've got analogies for. You can come up with some weak analogies, but it behaves in completely bizarre ways, because how do you transition from one wave to two waves? And when you can't be in between. See, try to picture that in your head. In an instant, a wave goes from one wave to two waves. See, you can't actually picture that, right? But the math says it works, and when you try it, it works. Yeah.
Does that theoretically prove that teleportation is possible?
Oh yeah. It happens all the time.
Does it?
Yeah, because it happens with electrons usually, is that when they're next to each other, there's a chance that electron can be found on the other side of that atom. And every once in a while it will be. So the electron leaves this atom and goes to a different atom.
Is that in study? Like we can study?
We'll go, we see what's happening. We watch it happen. We watch the electrons migrate.
Quantum
Quantum mechanics are weird.
Why are we learning this in 10th grade?
Because quantum mechanics is how the atom works. I'm just touching the surface of the weirdness. It gets really weird. The deeper you dive, the weirder it goes.
What if like different waves are all one wave? Just
Each electron is its own wave. Okay, so the quantum mechanical model still has energy levels. Okay, but they're not little circles. Okay, it's one whole wave, two whole waves, three whole waves. Peter, standing waves towards the front. Okay, so it does not have nice little circular orbits. Nah, they're freaky. No. When you see them, you will agree with me. Where the heck did that come from? Okay, but like I said, you can't solve it exactly, but you can find the probability of finding an electron a certain distance from the nucleus. The probability of finding an electron. Hey, we've already talked about that. That was our description of the electron cloud. He called. I don't think that Rutherford called it an electron cloud. I think that was added afterwards. That they said that because he just said they were outside, and our word for the electrons just outside is electron cloud. He just said they were outside. He didn't know how they were moving, because he didn't have anything. He didn't test anything that would tell him. Right? The alpha particles would not tell him about electrons. Just like a car will not help you find a water bottle. Okay? So that's where we got this picture. The electrons inside that blurry electron cloud. Where you have a chance of finding an electron. But here's the problem. If I tried to solve the math for electron on the end of in an atom on the end of my nose, being at the projector, I could do the math, and the probability is not zero. It's incredibly tiny, but it's not zero. So I am never going to get to 100% probability, because to get to 100% probability, I'd have to circle the whole universe. And that doesn't tell me very much information. Okay? So what they've decided is they will draw a line that contains 90% of the probability. So the electron cloud says 90% of the chance you're going to find an electron, 90% in here. Not 90% of the time, because it's not about time, it's about chance. And this is what Einstein hated. He says, you've got to be able to do better than say probability. His quote is, God does not play with dice. But all his arguments forced the other scientists to work so much harder to prove Einstein wrong that it drove the conversation and advanced the science. So being adamant and wrong and arguing is okay if it makes the other people argue back, as long as you're willing to listen to the evidence when they bring it back to you. You said this, now here's the evidence. Okay. So, what do they look like? Okay. Well, first of all, I want to say this: we had orbits before. Bohr had orbits, nice little circles. They like that name so much, but they're not nice little circles, so instead of calling it orbits, they call it orbitals. Orbitals and orbits are different things. Okay. And what describes them first is the principal quantum number. It's labeled n when they do it, and it's the energy level. So it turns out if you look at Schrodinger's equations, there's some numbers that show up. And just like you can tell the shape of a conic section based on the size of your coefficients for x squared, xy, and y squared, all you have to know is a, b, and c, and it'll tell you what shape that thing's going to be. There are the same kinds of numbers for atomic orbitals. There's 4 of them. We're only going to talk about the first one, but then there's the azimuthal quantum number, the spin quantum number, and the magnetic quantum number. 4 numbers that describe all those equations. So there's a pattern to the equations. Okay? And inside the energy level, inside that type of wave, there's more than one type of wave you can make. There's more than one way to make one whole wave. So in an energy level, it's built up of orbitals. Okay? Those are the orbitals. The atomic orbitals are the shapes inside the energy level. And the definition of atomic orbital is almost the same as the definition of the electron cloud. Okay? Because that orbital is a place where you have a high chance of finding an electron. Isn't that this definition we wrote for electron cloud just a little bit ago? What's the difference? Specificity. No, specificity. Atomic orbital is talking about a specific electron. Electron cloud is talking about all the electrons. So you put together an electron cloud by going through the energy levels and then seeing what shapes are in each one of those. So you build an electron cloud out of atomic orbitals.
Probably defining a
A specific electron. So there's specific versus all. So if you want to build an electron cloud, you build it one orbital at a time. Okay. Sometimes your book, they will call it a sublevel because it's not a level. That's energy levels. What's the breakdown below energy level? Sublevel. Okay, the orbitals are given letter designations. The first type of orbital that comes out of Schrodinger's equation is called an s orbital. Okay. Every energy level, there's one energy level, there's one s orbital in every energy level. So in the first energy level, the s orbital is a possibility. In the second energy level, you could have an s orbital. The third energy level, you could have an s orbital. Fourth energy level, you could have an s orbital. Not could have, you do. Okay. The shape is actually what you would expect. It's a sphere. S orbitals are sphere, but S doesn't stand for sphere. S stands for sharp. Because there's a whole group of lines. If you remember we looked at hydrogen and had a whole bunch of single lines, but you looked at helium and saw a whole bunch of double lines. That's because if you have if you have two electrons in helium, the first one, if it comes off, right, is going to come off a certain energy level. And then the second one from that energy level can come off. But it's going to have a little bit more energy than the first one because it's not being repelled by the first electron. So the second one coming off is going to be a little bit harder. Because the first one is getting pushed by its negative neighbor too. So there's two lines right next to each other. Okay? And that's how they know each s orbital can hold two electrons. So in the first energy level's s orbital, there's room for two electrons. In the second energy level's s orbital, there's room for two electrons. In the third energy level's s orbital, there's room for two electrons. In the seventh energy level's s orbital, how many are going to fit? Two. And the difference between the first, the second, the third, the fourth is size. This would be 1s, that'd be 2s, that'd be 3s. They get bigger because they're further away from the nucleus to have more energy. That still works. Like Bohr was right. Further away, he's going to have more energy. Okay? Rather than, and that's what we do. We don't say the first energy level's s orbital, we say 1s. Second energy level's s orbital is 2s. The third energy level's s orbital is 3s. And to say how many electrons there are, I can either put a 1 or a 2 as a superscript. The superscripts tell you how many there are. I will never write a number bigger than 2 next to s, because s can only hold 2 electrons. Okay with that? Hey, so you're going to have a chance of finding electrons close to the nucleus, then a chance of finding different electrons a little bit further from the nucleus, chance of finding different electrons a little further from the nucleus. You stop doing that when you run out of electrons to find.
So the only orbital that holds one electron is 1s?
No, 1s can hold 2 as well. All of them can hold 2. But if there's only 1, you write a 1. If there's 2, you write a 2. If there's none, you don't write it because there's nothing there. Okay? The second type of orbital is called a p orbital. Okay? And there's a set of lines. I forget what the P stood for those set of lines. I know it for the other two, but this one I forget which one it was. But it was another set of lines that they found repeating. And then they figured out that they were repeating because as that tied into Schrodinger's equation, because the two went together. Okay. There is no p orbital on the first energy level. There is one on the second, and on the third, and on the fourth, and on the fifth, all the way up. You can see that I've drawn 3 pictures. I had somebody else drew them and I copied them because my drawing's not that nice. Okay. Notice, what do you notice about those pictures? Are they different shapes? No, it's the same shape, just different directions. The first one is along the x-axis, the second one's along the y-axis, the third one's along the z-axis. Right? So it's got 3 different directions. Sometimes they call them shapes. It's really the same shape 3 different times. I think of it as 3 different directions. And the word they like to use to describe that shape is dumbbell because they're talking about weights. Weightlifting weights. They look sort of like that. Okay. And each of those shapes can hold up to 2 electrons.
Wait, so that's why there's only 2 elements in the first group?
That's what we're getting to. Okay. So there would be room for 2 here, 2 here, and 2 there. So in that energy levels p orbitals, I have room for a total of 6 electrons. Okay, and if that was 2p, 3p would be the same shape, only bigger. 4p would be the same shape, only bigger. Because further away is more energy. That still works. Okay. Now, remember, we're talking about specific. So those 3 p orbitals would actually be all at right angles to each other. But you would also have an s orbital. And you'd also have another s orbital. And they all lay on top of each other. And that's how you build an electron cloud. Okay? That you're going to find some electrons along this way. You're going to find a chance up to 2 electrons here. 2 electrons here, 2 electrons here, 2 in this area, and 2 in this area. 1 electron at a time, you can build the whole electron cloud. Okay. The next set of orbitals is called the d orbitals. That's for diffuse, another set of lines. Okay, now, have you seen you should be able to see a pattern now. So s orbitals started on the first energy level, p started on the second, d's will start on the third. So we call it 3d, then 4d, then 5d, then 6d. S has had 1 shape. P's had 3 shapes. 1, 3, 5 shapes. And there are the 5 shapes. 4 of them look like clovers that are just oriented differently. And the 5th one looks like a p orbital with a donut around it. Okay. So each shape can hold up to 2 electrons. So that means my d orbitals can hold a total of 10 electrons. At most. There's room for 10. This is outside the nucleus. This is where the electrons are going to be found. That's all we're studying now is the electrons. We're done with the nucleus.
Wait, what do the different shapes represent?
That's okay. So you have a chance of finding 2 electrons in this area. You have a chance of finding 2 electrons in that area. Chance of finding 2 electrons there, 2 electrons there, and 2 electrons in here someplace. So that's where you're going to find a chance of finding a total of 10 electrons. It's a solution to Schrodinger's equation. Schrodinger's equation draws those shapes. And then they test them, and it works. Okay? It works. Okay. Next shape is called F for fine, because there were some really skinny lines, fine lines. Okay, actually it's a p orbital with 2 donuts, one on each end. Okay. So it's got the p orbital, but then it's got a donut around each side. Technically, that's called a toroid. When you learn polar coordinates, you'll learn the equation for a toroid. Okay. We should be able to fill in the next few lines, right? It starts on the 4th energy level. 1, 3, 5, 7. I couldn't get all 7 on the screen. These are 3 that look alike. Each holds up to 2 electrons. So if you've got 7 shapes and each has room for up to 2 electrons, that's a room for up to 14. But I want to give you an idea that this is really about waves and repeating pieces. And I can do that just from the pictures. Okay? There's 3 of the F's. The other 4 look like this. They look like jacks, 8 different directions. But notice the pattern in the shapes. When I started off with S, there was just one big shape, right? When I went to P's, split, now I got 2 lobes. Okay? And then when I went to D, most of them had 4 lobes. So, and then when you get to the F's, it's 8. You see how waves would do that? You cut them in half so you can make a whole wave. Right? So, here's what you should have taken out of that discussion. Okay. Numbers and numbers you need to know. S has how many shapes? 1. So the maximum number of electrons you can fit into it is 2, and it starts at energy level number 1. Okay. Hey, number of shapes for P? 3 shapes. Maximum number of electrons? 6. Yeah, 2 for each, so that's 6. And starts at energy level number 2. D? 5 shapes, 10 electrons, 3. F's? 7, 14, 4. Okay, now, we're only going to need up through the F orbitals. The next orbitals go in alphabetical order. Next comes G. For G, how many shapes would there be? So it could hold a maximum of, and you wouldn't see it till energy level number 5. See the patterns there? Hey, hey, I've seen some of that before someplace. Oh. That's why that's been staring you in the face all year. I just listed all the orbitals we could talk about. There's the 1s, the 2s, the 2p, the 3s, the 3p, the 3d, the 4s, the 4p, the 4d, the 4f. So all those orbitals we just talked about, they're right here. 1s, 2s, 2p, 3s, 3p, 3d, 4s,